What's good, everybody? I'm just going to do a little experiment right now. So, let's pump some gas particles into this container. And as we know, gas particles, they kind of take the shape of their container. So, I'm just going to let these gas particles kind of bounce off of each other. You can see what's kind of happening here. Some gas particles, like this one, are faster than other gas particles, like these ones, as you can see. And I want you to pay attention to one specific gas molecule. Gas particle. One gas particle. I'm just following this one. And you can see that it travels in a straight line. Except when it hits another gas particle, or except when it hits the wall. Now the pressure right here, well, this gas pressure is basically kind of the pressure when these sort of particles, they hit this container. That's what's kind of going on here. It shows the pressure when the gas particles hit the container. So what I'm going to do is I'm going to keep the volume constant. So the size of this container is going to stay the same. And what I'm going to do is I'm going to raise the temperature, and then after that lower the temperature to kind of see the trends in this experiment. Let's go. Heating up. I'm going to heat to 700. Alright, just a little higher, but okay. 740. Look at the pressure now. Whoa, the pressure is much higher than before. But why? Why would the pressure be so much higher than before? The amount of gas particles stayed the same. Well, you could take a look at the gas particles now, and you can see that most of them are traveling faster than, when we just originally started. So, we could say that one thing that changed is the average kinetic energy of these gas particles increased. And why? Why do we say average? Well, it's because some gas particles are still moving really slowly. But it's like the majority, it's like this whole thing. You can see most of it is moving faster than when we started before. So we say the average kinetic energy increased. Now let's see what happens when we drop this. Okay, I'm just going to go, let's say 50. I'll do 50. Okay, you can see it gets really slow. Yeah, much slower than before. And you can see that, well, these gas particles, they don't have this much kinetic energy. So when they don't have this much kinetic energy, well, they don't hit the wall as often. While you saw them before, when the gas particles, when the temperature was super high, these gas particles were faster, and therefore they hit this wall of the container more, resulting in more pressure. So we could say that temperature and pressure are proportional. So why do we say it's proportional? Well, if the temperature goes up, the pressure goes up. If the temperature goes down, the pressure goes down. So let's restart this experiment. So I'm going to go back to 300 Kelvin. And that's good enough. I'm going to hold the temperature constant. So the temperature is always going to stay in 303 Kelvin. And right now we can see this pressure. It's between 6.2, 5.5. So the average is just 5.8. And let's see what happens when we expand this container, okay? So we increase the volume of this container, and look what happens. Whoa. Somehow, the pressure got smaller. So the amount of pressure the gas particles are exerting is smaller. But why? Why? The particles are traveling at the same speed. So why would the pressure be lower? Well, this is because, think about it like this. Think about if you're in like a race, okay? And say hitting the container is the finish line. This container, you starting from here, hitting like this container is the finish line. Well, it would take longer to hit the container from here to here than from where we originally started, which was here to here. So you could see, because the container is bigger, it takes longer for these particles to travel and hit this container, resulting in less pressure. Let's decrease the volume. Let's see what happens. Whoa. Okay. It's about 12. I'm just going to keep the average at about 12. And look at that. The pressure is way higher. And once again, using the logic from before, this is because, well, since the volume of this container is less, it's going to take less time for these particles to travel and hit the wall. So it's like doing a 50-meter dash compared to doing a 200-meter dash. You're going to get to the 50-meter faster than if you were to do a 200-meter dash. Okay, let's return to our original size. And now let's make the pressure constant. And before we start the pressure, this part, one thing about the volume and one thing about temperature is that, well, if the temperature stays as constant and you have the volume and the temperature, as the volume increases, we can see that the pressure decreases. And as the volume decreases, the pressure increases. So this is why volume and pressure, they're kind of inversely related. So inversely proportional. Because, well, when one thing goes up, the other thing goes down. Other thing goes up, that thing goes down. And now we are going to start. So we are keeping pressure constant. And we're just going to heat things up. And whoa, you could see. Sorry. Well, you can kind of see what's happening here. If we want to maintain a constant pressure, we would have to raise the temperature and we would have to increase the volume at the same time. Why would we have to increase both? Well, think about it. If we want this pressure to be constant, and when we increase the temperature, these gas particles, we know they're moving faster. Which is why we have to kind of increase this volume of the tank to balance this out. See, it's like if I were in a race with Usain Bolt, to balance things out, I would do a 100-meter dash and he would have to do a 200-meter dash. So this kind of is like the same concept. Since these gas particles, they're now faster because of the temperature, well, they're going to hit the tank faster if this volume was the same. So, which is why we have to increase the volume when the temperature goes up. Let's see what happens when we cool things down. Okay, we're cooling things. Whoa, okay, sorry. Let's cool things down. So the pressure, you can see, the pressure's staying the same. Let's cool things down. Okay. Now you can see, wow, this is literally the same logic that we used before. Because the particles are traveling way slower, the average kinetic energy is slower because of the temperature. We have to decrease the volume because then the gas particles can actually maintain this pressure from hitting this. Otherwise, if the volume was like this big, well, it would take the gas particles way too long to actually hit the container, resulting in not a constant pressure. So you can say that one thing you can say that the volume and the temperature are proportional. So when this pressure is constant, when the volume or if the temperature increases, the volume also increases. You can see the volume also increases as the temperature goes up. If the temperature goes down, the volume decreases. So this is why they are proportional to each other. So this is just a key summary of everything we did. So when the temperature goes up, the pressure goes up. And this is because the gas particles, they move faster. So there's more kinetic energy in the gas particles, making them collide in the container more. And when the temperature goes down, the pressure goes down because the gas particles don't move that fast. So they're not going to collide in the container as that much. So this makes temperature and pressure directly proportional. So this is where the temperature is constant, aka the speed of the gas particles stays the same. When the volume of the container increases, the gas particles will take a longer time to collide with the container, making the pressure lower. And when the volume of the container decreases, the gas particles, they don't really have to take that much time to collide with the container, as the container is super small. So this is when the volume goes up, the pressure goes down. But when the volume goes down, the pressure goes up, which makes them inversely proportional. And this is when the pressure is constant. So when the temperature increases, gas particles move faster. So to keep the pressure constant, the volume also has to increase. Just like how I have to increase the distance for a race between me and Usain Bolt to kind of keep the time finishing the race fair. So as the temperature decreases, the volume also decreases, which is why temperature and volume are directly proportional. Hope y'all enjoy the video. Sorry for the sirens. Have a nice day.